Hello everyone. In this video we are going to see about this NP hard and NP complete problem. So before going into that, first we should understand what this polynomial time algorithm is. So an algorithm is said to be solvable in polynomial time if the number of steps required to complete the algorithm for a given input is big O of n power k for some non-negative integer k, where n is the complexity of the input. So what is given here is the running time of an algorithm. So that is what the main thing that we are computing in an algorithm. So if the running time is upper bounded by an polynomial expression, a polynomial is nothing but what we have seen here. It consists of the variables, coefficients, the constants, and the exponential values. So this includes the operations like addition, subtraction, multiplication, and division. And here the exponential cannot have a negative value, so it should be a non-negative constant. And so if any algorithm uses only a polynomial amount of computational resources, then we can say that that algorithm is an efficient algorithm. And so the running time of any algorithm can be given by the big O notation, that is the upper bound value. So big O of n power k for any positive constant k. So now, since the algorithms that can be solvable in this polynomial time are said to be efficient algorithms, or it could be, or those problems can be solved efficiently. Now the most familiar mathematical operations such as this addition, subtraction, multiplication, division, and also the square root computation, powers, logarithms, all these operations can be performed very well in polynomial time. Now, as this polynomial time concept has been coming up, it leads to several complexity classes in this computational complexity theory. So, the main complexity classes that we are going to discuss here is P and NP. So, what this P class tells about the complexity class of decision problems that can be solved on a deterministic Turing machine in polynomial time. So now we know what this polynomial time is, and the decision problem is nothing but the problems where the answer would be either an yes or no. So for these kind of decision problems, the if that could be, if these kind of decision problems, if it could be solved using a deterministic Turing machine in polynomial time, then we call that class of problems as P complexity problems. And another category is this NP complexity problem. So in NP complexity decision problems, here it could be solved using a non-deterministic Turing machine in again polynomial time. So we'll discuss about this in detail. So the P class problems. Now these are the class of decision problems that can be solved very efficiently, and it could be solved in polynomial time. For example, if you take normal multiplication of two numbers, so if the number is 2-digit value, then it will require n square single digit multiplications. We know that. So if you are multiplying two-digit values, then it has to do 4 single digit multiplications. So this is again a polynomial in n value. So this problem, it could be easily solved, and we have the efficient algorithm for that. Now here there are a list of algorithms that works in polynomial time, and another list of problems that works in exponential time. So this searching and sorting and this matrix multiplication, all these algorithms, if we can see, the running time of these algorithms could be either n log n square, or n log n, and so on. So that means this could run in polynomial time. And if you take the problems like 0-1 knapsack, or traveling salesman problem, sum of subsets, graph coloring, so these problems, you can see that the time required for running this algorithm could be in exponential time, 2 power n. So here for all these problems, this knapsack or TSP, sum of subsets, for all these problems there is no polynomial time efficient solutions. So there are two things that we can do about these problems. So if the thing is here we can find a association between all these problems, instead of solving one particular instead of solving for every problem, we could find an association between all these problems, and if one problem could be solved, then all the other problems can be easily solved. And the next one is, if there is no deterministic solution for these kind of problems, then we can try for a non-deterministic solution. So there comes the class of NP class problems. So this NP class is a class of computational problems for which the solutions can be computed by a non-deterministic Turing machine in polynomial time. So one thing is, so this NP class can be called as the solutions can be computed by non-deterministic Turing machine in polynomial time, or otherwise this can also be called as for these problem instances. So these are a set of decision problems for which the problems for which the answer is yes, we can have the proofs verifiable in polynomial time. So let me explain what it is. So though we don't have a proper algorithm or a proper solution for this kind of problems, if a potential solution is given, we can just verify it whether it is correct or not, and that verification can be done in polynomial time. Let us see an example. So it is an example of a partition problem, and the input is given as a finite set of natural numbers, the set given as yes, and the question is now whether it is possible to partition this set yes into two sets A and B, so that the union of these two sets will be equivalent to yes and the intersection will be equal to phi, and the sum of the numbers in both the partitions should be equal. So this is the equation. Now for this problem we don't have a proper solution. We do not know how to solve this problem. That is, when a set is given, we do not know how to partition it into two sets so that these conditions can be satisfied. But if I am giving you two sets A and B and a set yes, and if I ask you to check whether this condition is satisfied, then that can be easily done. For example, you see here the set yes is given as 1, 2, 4 and 5, and two partitions were given, A and B, where A is equal to 2, 4 and B is equal to 2, 5. Now now a solution is given. Now a solution is given for this problem. So a set of natural numbers is given, and partition of this set is given as A and B, two sets two partitions were given with a. Now we can easily verify whether the given solution is correct or not, whether it is a right proof or not. So if you see that the sum of these two numbers is 6 and the sum of these two numbers is also 6, and the union of these two sets gives you the actual set S, and intersection of these two sets is equal to 5. So now we can verify this particular solution is correct and the proof is true. Now let me give you another example with the same problem. Now A is given as 2, 5 and B is given as 1, 4. Now here we can see that the sum of these two sets, okay, here the sum is 7 and here the sum is 5, so this is not equal. But we cannot say that this is not the answer for this solution is answer for this question is no, because the question asked is it possible to partition S into two sets so that this condition is satisfied. Now a solution is given. Now based on this solution I cannot say that this S cannot be divided into two sets to satisfy this solution, because there are several other solutions through which I can prove that it is possible. Because in the first solution we can say that yes, there is a possibility for partition of the set into two sets, and the union of these two sets can be combined into the set S, and intersection can be again 5. So that and all can be proved using some other solution. So here our intention is, when a solution is given, we can verify whether that solution is true or not, whether it is right or not in polynomial time. So that is what called as this NP problem. So here we can read it again. A problem is in NP. If given a potential solution, we can verify that it is correct or incorrect in polynomial time. So this is called as the NP problem. So P problems are efficiently solvable and NP is efficiently verifiable. So P is equal to NP if and only if the problems that can be efficiently verified are the same as the problems that can be efficiently solved. Now coming to NP hard problem. So as we have discussed, for any efficient algorithm, the minimum requirement is that it should run in polynomial time, that is big O of n power k. And not all the problems can be solved this much quickly. So what this NP hard problems are, it is at least as hard as the hardest problems in NP. So now we have seen what NP problems are. So it could be easily verifiable in polynomial time. So now in that, the NP hard problem is defined as it is at least as hard as the hardest problem in NP. So an example of this NP hard problem can be a subset sum problem. And the important thing about this NP hard problem is that this need not be in the among the elements of NP. This need not be come under the category of NP problem at all, and they may not even be decidable problem also. So this need not be a decision problem, or it need not come under the NP problem also. The next one is NP complete. So when we can say a problem is NP complete is that if it is both NP hard as well as an element of NP. So if it is both NP hard as well as an element of NP, then we can say that the problem is NP complete. So here we can say that the NP complete means the problem is at least as hard as any problem in NP. So in NP complete, it should be present in NP, and among the NP problems, the hardest problem is called as the NP complete. So it is a class of decision problems which contains the hardest problems in NP, or the most difficult NP problems, and definitely it has to be under the category of NP problems. So here, as we saw earlier in that list of exponential problems, so even if one problem can be solved, then all the other NP problems could be solved. So this is what NP complete problem is. So we'll see one example, a circuit satisfiability problem. So what this problem says is, we do not know how to solve this problem in polynomial time, because what the problem is, the input is a set of Boolean values. So input to this circuit is a set of Boolean values, true or false values, either it can be 1 or 0, and output should be a single Boolean value. Now the question is, what the requirement of this circuit satisfiability problem is that whether we can find an input that makes the circuit always false, or conversely we can ask whether the circuit always outputs false for a particular input. So what it is asking, whether we are able to find such input that gives always an true output, or always gives a false output. But for finding a solution for this, definitely we need to go through all possible solutions, all possible inputs, all possible 2 power m inputs to the circuit, but definitely that will require exponential time. So what we can do is, here when a solution is given, when I give, for example in this particular circuit, when I give some values for x1, x2, x3, x4 and x5, we can definitely say what the output is. So I can verify whether for this particular set of input the output is true or not. So this comes under the NP complete problem. So we will not be able to give a solution in polynomial time, but we can verify the solution in the polynomial time when a solution is given. So this is an example of a NP complete problem. So we need to understand what a polynomial time is, and what the decision problem is, and what P problem, what the NP problem, and what NP hard and NP complex complete problem is. Thank you.